Alrighty, so we said that atoms want to satisfy the octet rule, meaning they want to have 8 valence electrons, either shared or unshared, and that's why they do covalent bonding. However, there's some atoms that do not want to follow the octet rule, or cannot follow the octet rule. Some atoms are just too small, so 8 electrons is just way too many for those atoms to hold, either sharing or unsharing. So they'll do less than the required 8. Then there are some atoms that are actually large enough that they can accept more than 8 electrons. So they'll go beyond the octet rule. So they can hold 10 electrons, 12, so they can do that. So those are the exceptions to the octet rule. So here's a couple right here, and we'll do some examples in this video as well. First we have hydrogen. Now remember, hydrogen only has 1 valence electron. So it can only hold up to 2. It can pair up to someone else, to another atom, and there you go. That's it. So hydrogen only have 1 bond. Beryllium, if you look at beryllium, it has 2 valence electrons. So it just has 2 bonding sites. So it can only hold up to 4 valence electrons. Boron has 3 valence electrons. So as you see, it only has 3 bonding sites, 1, 2, and 3. So you're going to hold up to 6 electrons. And now the other atoms, some atoms are large that they can hold more than 8 electrons. These are some examples here: phosphorus, sulfur, and xenon. And there's actually a lot more, which we'll go over today too. Phosphorus can hold 8 or 10 electrons. Sulfur can hold 8 or 12. Xenon can hold 8 or 12. And actually, both of these can also hold 10 as well if needed. So here's some examples down here, and we'll sketch these out for you. So this is sulfur hexafluoride. As you see, sulfur has 1, 2, 3, 4, 5, 6 shared pairs of electrons. That's a total of 12. Here's phosphorus triiodide or pentiodide. 1, 2, 3, 4, 5. So that's 10 electrons there. Xenon tetrafluoride. 1, 2, 3, 4 shared pairs of electrons. That's 8. It also has these 2 pairs of unshared electrons. That gives a total of 12. Right. So now if we look at these, so let's look at 2 compounds here. We'll look at NF3, PF3, and PF5. Okay. All right. So we look at NF3. Okay, well, nitrogen has 5 valence electrons, and fluorine has 7 valence electrons. So if we put those together, here's our nitrogen in the middle with our 5 valence electrons. As you see, there's our 3 bonding sites. Each of them will attach to a fluorine. 1, 2, 3, 4, 5, 6, 7, and then there you go. Here's another fluorine. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right, there's NF3. So PF3 kind of looks like the same thing. All right, you got phosphorus with its 5 valence electrons, and then fluorine. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 4, 5, 6, 7. All right, there you go. So, all right, so those both satisfy the octet rule. They have 8 electrons. All right, so normal stuff. Now PF5 goes something like this. So the first 3 fluorines, just like we did above here. All right, so no different than PF3, okay? But now there's just 2 extra fluorines there, so they need some spots. When you look here, we got this unshared pair of electrons here. So what will happen here, and we get a hybridization in another video, we'll explain how that happens. But what happens here is these two electrons will actually split up and become two new bonding sites. So now they're not paired anymore. They're alone and looking for bonding somewhere else. So 1, 2, 3, 4, 5, 6, 7. So there you go. 2, 3, 4, 5, 6. And that's PF5. All right. So, yeah, so if you have to hold more than 8 electrons, then typically your unshared pairs of electrons will split up and create new bonding sites. All right, so SF2. Well, if we look at that, sulfur has 6 valence electrons. Here's fluorine, 1, 2, 3, 4, 5, 6, 7. There's your other one, 1, 2, 3, 4, 5, 6, 7. There's SF2. So, try SF4. Alright, S, and again it's 6 valence electrons. Well, there you go. That's SF2. So now, where do you think the other 2 fluorines are going to go? And yeah, so a pair is going to split up. Now it can either be this pair or this pair. It really technically doesn't matter. Okay? So we'll just do the left side here. So those are going to split up the bonding sites. Now, what's not going to happen is that. Okay, that's not going to happen. Okay, so when a bonding site or when a pair splits up, they become bonding sites. You don't take one electron from one pair, one electron from another. It doesn't work that way. So we're going to split up that one. 3, 4, 5. And then there you go. That's your SF4. And SF6. All right, you probably figured this one out by now. There's 1, 2, 3. Oh, I forgot my electrons here. 1, 2, 3, 4, 5, 6. There you go. SF6, sulfur hexafluoride. So in each one of those, we need to add some more atoms. We split up the unshared pairs, and that made some more bonding sites. Okay. Now, so why this happens? It has something to do with the atom itself. All right, so we showed you before. All right. So phosphorus can split up and add on 2 more bonding sites. However, nitrogen can't do that. All right. Now, the reason for this. All right, let's look at the electron configurations. Okay. Nitrogen's 1s2, 2s2, 2p3. All right. Phosphorus, I'll show you a periodic table here. Phosphorus is 1 below. Okay. So it's almost exactly the same, but it's 1s2, 2s2, 2p6, 3s2, 3p3. All right, so if you look here, your valence shell is second energy level. Here, valence shell is the third energy level. All right, now What does a third energy level have that the second energy level does not have? Yes, you guessed it. 3D orbitals. Okay, you got 3D orbitals present. Technically, you can say it's 3D0 because there's no electrons in there. All right, but that 3D orbital, that is where extra electrons go. So when these bonding sites split up and take on those extra electrons, they'll go in this extra d orbital. Right? Nitrogen, since the second energy level does have d orbitals, it cannot create those extra bonding sites. So there you go. So really, if you look at the periodic table, okay, nitrogen, oxygen, fluorine, okay, those they can't go beyond the octet rule because these are in the second energy level. There's no 2d orbitals that exist, so can't hold those extra electrons. Okay, but if you look here, silicon, phosphorus, sulfur, chlorine, arsenic, selenium, all these are in the third energy level, fourth energy level, fifth energy level. They all have d orbitals available. They're empty, but they're available. So these can take on more than 8 electrons. Right? So it's not just sulfur and xenon and phosphorus. It can be any. So like for example, we can have, let's pick a good one here. We could pick bromine, or let's do tellurium. Whoops. Tellurium iodide. Okay, if you look at tellurium, here it is under sulfur, 6 valence electrons. 1, 2, 3, 4, 5, 6. There's an iodine there. There's an iodine there. And then, so now you need 2 more iodines. Oh, there you go. Voila. All right. Another example. Iodine, I3 negative 1. This is a triiodide ion. All right. So if we look here, all right, there's your iodine there. There's 1 iodine. So if we put another iodine here, you got that. So that's your I2. That's your regular, typical, run-of-the-mill iodine molecule. All right, remember, this is I3. We're sticking in this third iodine atom here. Okay, so that's got to go somewhere. So where are we going to do that? That's where, with iodine being a big atom, it can split up some bonding sites. So for right now, we can pick whichever one we want. All right, I'm going to do, let's do this one over here. So this one's going to split up. So that's going to split there, and that's going to split here. Well, that's good. That'll take on the other iodine. All right. But now what happens is this one doesn't have anything to bond with. That's where this -1 comes in. So the -1 means that, yeah, it's gaining 1 more electron. So that's just going to pair up with that other one right there. And there you go. There's your I -1. And since it's an ion, got to put in brackets. There you go. So those are some examples of extensions or expansions of the octet rule. So just remember, anything that has possible d orbitals, which is essentially silicon, phosphorus, anything greater than these elements here, all these down here. All right, if they have potential or possible d orbitals, they can hold more than 8 electrons. And all you have to do is, just like with everything else, just break up some bonding sites, or break up some shared pairs of electrons, and those become bonding sites.